So our next speaker is going to be Tom Hoffman. Tom is a 30-year veteran of JPL. He's worked on a number of missions there, a number of Earth observation missions, the Grail mission, Spirit, Opportunity, and now he is the project manager for the InSight mission, which is currently on Mars, looking into what's underground on Mars, because you know most of Mars is underground. So there it is.
We get to watch my file download here for a second, so that's very exciting. Yeah, so it's got a lot of cool stuff, and I'm really excited to be back here. I was here about a year ago at the last meeting that you had, and it was just a little bit before launch, and that's a very trying and nervous time for anybody trying to get to Mars, because it's not easy to get to Mars, and you guys know that better than just about anybody else on the planet. A lot of the missions that we plan to get there, whether they be orbiters or landers, just don't make it. And so I'm happy to report that I'm here, which must mean that we made it, which is a good thing. With no further ado, let's start talking about InSight. So InSight is it's a unique kind of mission. It's not in the strictly in the Mars program, which is the Follow the Water, which is the theme that we've been doing for years now. It's a mission that's really designed to look deep inside the interior of Mars. And maybe this is working. Oh, there we go. So we've seen a lot of stuff from the surface, great pictures from the Mars Reconnaissance Orbiter of dust devils and even some landslides and all kinds of really, really cool stuff. But we know precious little about what's inside Mars beneath the surface. And so that's what the goal of this mission is. It's going to look deep inside the interior of Mars to understand how did the planet both evolve over time and initially form. We believe Mars, Earth, all the rocky planets formed the same way, started their evolution very similarly, but then things changed. Venus is very different than Earth. Earth is very different than Mars. We believe that possibly that answer to why that happened lies within the interior, and trying to understand the interior may give us an idea of not only what's going on with Mars, what may go on with Earth, and very excitingly, what may be going on other exoplanets around other systems. So that's the basic goal of this mission. And so here's our timeline, kind of an update on that. So we did launch May 5th of 2018 as our first ever interplanetary launch from Vandenberg Air Force Base. We successfully landed November 26th, Elysium Planitia, which is very near the equator, because we are solar powered, not nuclear powered, so we wanted to get as much sunlight as we can all year round. Very interestingly, for the very first time, we actually had to take instruments off the deck of the lander using a robotic arm and place them onto the surface of Mars. And so we finished that deployment. You can see it was quite a bit after we landed, and I'll explain why that is, but we finished it February 28th of this year, and now we're there gathering science, and we have been since that date. So let me show you this picture. I think you're going to have to click on something. Yeah, so click on this. This is our landing day video. So obviously I was here and I've seen it a few times, but it's pretty gosh darn exciting.
InSight has passed through peak deceleration. Telemetry shows the spacecraft saw about 8 Gs. InSight should now be experiencing the peak heating rate. Ground stations are observing signals consistent with parachute deploy.
Marco Alpha, Marco Bravo, maintain launch status.
Altitude convergence, the radar has locked on the ground.
Yes.
Standing by for lander separation. Lander separation commanded. Altitude 600 meters. Altitude 400 meters. 200 meters. 80 meters, 60 meters, 30 meters, 20 meters, 17 meters, standing by for touchdown. Touchdown confirmed.
Yeah, so that was a really, really good day. That was a lot of fun. I mean, it's one of the few things that really brings people from all around the planet together. I think everybody is truly excited about landing on another planet. And just imagine when that's actually people. That would be so amazing, I think. So when we landed, we got this very first picture down, which you can tell is a little bit hazy, and that's because we actually blew up a fair amount of dust. You saw the rockets in the animation. Blew up a fair amount of dust onto our dust cover. So we flopped the dust cover, and it really didn't look too much different, which was kind of unfortunate for us. But eventually we got our arm out, and we took a picture, and because we were a celebrity, we had to get a selfie. Every good celebrity takes a lot of selfies. And we posted, of course, on social media. So this is our first selfie of the InSight lander, and you can see there's it's kind of an oblique, weird angle because of the way we took the pictures. But here's our seismometer, here's our wind and thermal shield, here's a picture of our heat flow physical properties package, and a bunch of the solar arrays, obviously, and then all the other items on the deck. I'll talk about more of those in just a minute. But I wanted to show this picture here. So here are our payloads. So we have, for the very first time, interestingly, put a weather station on the surface of Mars. So we have pressure measurements, temperature measurements. We're doing magnetometer measurements, which have given us some interesting results to date. And we also, so those are all mounted here on the deck of the lander. We also have a seismometer, which is our main instrument that we flew. And so that's actually looking at Marsquakes to understand what the structure is of Mars. And then we have a heat flow physical properties package that I'll talk a little bit about because we've had some trouble. This is a great picture showing us way down here. Unfortunately, it's still about here, and I'll talk about what we're doing to solve that. It's been a very, very interesting engineering challenge and one I've been excited to be part of. Go mole! Yes, absolutely. Save the mole. All right, so here's what our next step after we landed, which we call entry, descent, and landing, or EDL. We had to go through a second EDL, so we had to take those instruments off the deck of the lander and place them onto the surface of Mars. And this is the process that we used, and very quickly. I wish it went this fast. So we first took the seismometer off and set it onto the surface of Mars. And then, because seismometers are very good at measuring all kinds of different noise, we wanted to try to insulate it with this wind and thermal shield to try to get as much of the wind and the thermal variations on the surface of Mars out of our measurement. So we placed that on there next. And then we took the heat flow physical properties package, which has a self-hammering nail in it, aka the mole, and put that on the surface of Mars. And I really wish it happened anywhere near that fast. But as it turns out, that took actually 87 sols to do all of that activity. Because the very first thing that we did when we landed, we got a bunch of pictures back, and we have a test bed at JPL. Here's our mock-up of our lander. Not much of it's the same as the one on Mars, except we have an engineering model of the arm. So it has the same dimensions, much the same capability. And then we have weight models of each of the different elements that we need to lift with that arm on Mars. And so you can see we've put some boards down. We have, in this picture, we have hollow lenses, so we're using virtual reality. After we'd gotten pictures back from Mars, we created a digital elevation map. We had to recreate the terrain in front of the lander. Luckily, it was very benign, so there weren't a lot of rocks or obstacles, so that made it pretty quick to do. But we measured stuff out. We made sure that we had that slopes and everything else as close as we could before we started doing a lot of practicing of doing the deployment on Earth before we practiced it on Mars. So it actually took us about 22 sols to get all of that straightened out, figure out exactly where we're going to put the instruments, and then do our very first deployment, which you can see. Oh, this is us taking pictures, and then this is our very first deployment of the seismometer. It happened pretty quickly there, so I'll let it run one more time. Okay, and then actually this is the whole thing. So this is the, now we've put that down there, and it took us another like 40 sols to put the wind and thermal shield on because we wanted to make sure we knew exactly where it was. And now we're trying to move the tether back because one of the things that we need to do is open a gap up with the tether so that the noise from the tether doesn't perturbate our seismometer. So that took us quite a bit of time. Then we put the wind and thermal shield on there. You can see there's a grapple here that we're using to lift everything. It's basically got 5 fingers like a hand does. It's wax pellet actuated. And now we're going to be putting down the heat flow physical properties package, and that's our deployment. And again, it seemed like it went really fast, but that was actually 87 sols. We spent a little time getting the grapple undone, and then that was the end of our deployment of each of the elements. During that time that we were deploying, it's going to run again here, so you can see there's still a fair amount of dust in these pictures, but over time, if you start looking closely, the dust starts disappearing. We think that was due to winds blowing the dust off there. So you can see here that we also dropped the tether at one point. So there's a lot of stuff going on in those pictures. I'm not going to keep showing it, but you could keep finding all kinds of cool stuff happening. So now we took another selfie. This time you can see the instruments are all off of the deck. So yes, indeed, that's secondary proof that we did deploy all of them. And so that was good. But you can also see, Dave would know this, but there's now a lot of dust on our solar arrays, so we're not getting nearly as much energy as we were. The very first day we landed, we got 4.6 kilowatts of energy, which set a new record for most energy on Mars. By this point, we were down to probably about 2,200, and today we're about 1,900 watts. So it's definitely been dropping. We've been steady there for quite a while, though. But it would definitely be nice to have more energy. So one of the cool things, though, is because of those sensors that we have, we're getting daily weather reports from Mars. This is from a little bit ago, but you can go on the web and see what the weather's been like. We also have not just temperature, the lows and the highs. We also have wind information, so you can see when the windy times of the day are. Not surprisingly, it's in the daytime and tempers off once the sun sets. But it's kind of interesting to see how the wind changes. We've actually detected several dust devils coming over our spacecraft. We have yet to image one. We've tried to image them, but those are really hard to get an image of. But we can tell from the pressure changes that we can see those happening. So here's our seismometer. So a little bit more in depth of what we're trying to do here. So it's an evacuated container. It has 3 very broadband sensors, very much like sensors that we have in Earth terrestrial seismometers. We also have some solid state sensors. This is one of them. So each of those are 3-axis, so we get multiple signals. And from that, we can detect what's going on. They're incredibly sensitive. They can detect motions in the ground surface of less than half the width of a hydrogen atom. And so one example I use, I think this audience probably understands that, but some audiences don't. And so if there were butterflies on Mars and one of them landed on our detector, it would very, very easily detect that. That'd be a huge signal, actually, for this. And that's a cutaway view, so you can see how it actually, here's that tether that's going back to the spacecraft. Here's the wind and thermal shield. We have another thermal shield around the actual evacuated container here. And we have legs I didn't talk about, but those actually level out the system. And then we have another leveling device within each of the sensors because they want to be exactly parallel with the ground. So how does that work? If we get a Marsquake, it generates a signal. And as that signal transmits through the planet, it bounces off different layers, so the mantle, crust, core, and any differences within each of those. And it creates this complex, very pretty, but complex set of signals that give us basically kind of an ultrasound of what's going on in Mars. And with enough of those built up over time, we can actually figure out what the structure of Mars is. So how does that work for our lander? Here's where we are. Here's that same Marsquake, and here's what we see on the surface of Mars. So the very first signal is typically the largest of all the signals. As the wave transmits its way through the Martian planet, it bounces around, it reflects, it refracts, and eventually those signals start coming back to where the lander is. And by looking at the amplitude, the differences in receive time, you can build up over time a catalog of what the seismic events are. And so to date, we've actually seen 150 seismic events on Mars, which is a pretty large number. It's actually larger than we would expected, but interestingly, they typically are smaller. So there's like 23 of them, which we know absolutely are beyond a shadow of a doubt a Marsquake. but only about 3 of them which are larger than the equivalent of a magnitude 3 on Earth. So it's very many Mars quakes, but kind of less substantial than you might expect. So the scientists, of course, love when they find something that's a little bit different than what they expected, because it makes them go back and think some more, and that's what scientists like to do. So for them, that's great. This one, this one you might have to click on as well. This is our first recording of wind on Mars. We actually were able to record it with our seismometers, and it shifted a little bit up an octave. Then this is going to be a Mars quake. And then just for fun, we hear the robotic arm, which is super trippy. Exactly, yeah, it's like a whale or something, yeah. Yeah, so that's actually detected from the seismometer sitting on the surface of Mars. So it's kind of interesting how that, even the robotic arm motion gets transmitted through the ground. Here's just for anybody who's a scientist and wants to look at what our spectrum looks like. So here's a picture of what our not quite so recent, but some of the major seismic events, what they look like in a spectrum. This kind of came out a little fuzzy. Sorry about that. So let's talk about our heat flow physical properties package. So that's essentially a self-hammering nail. So it has this support structure. The tether goes back to the electronics on the lander, just as with the seismometer. And the goal of this is to hammer about 3 to 5 meters into the surface of Mars. It does that with a really cool mechanism I'll show on the next page. But the whole point of this is to pull behind it the science tether, which has thermocouples embedded in it. And as it goes down, it sends out a heat pulse, and that heat pulse, it waits to see how long that heat pulse dissipates before it hammers down again. And by creating sort of a topology of what the heat conduction is of the soil as it gets down to depth, and then starting to look at each of the thermocouples over time, it can actually determine what the heat flux is. So you have the thermal conductivity and you have the heat, so you can get the heat flux. It's a pretty simple measurement, but that essentially tells us how active the core of Mars still is, how much energy, how much heat is still in it, how alive it still is. So it's actually a very interesting experiment. Just kind of as an aside, both of the seismometer and the heat flow experiments were ones that were prioritized for the Apollo missions. We actually had a deployment system called an astronaut in that particular case, and they put seismometers and a heat flow probe on Mars, on the moon to measure the same features on the moon as we are on Mars. So here's an animation of what I just talked about. So it's an interesting device. It has you'll see a winding up of a mechanism against a spring, and then that spring activates a mass. That mass bounces down and basically buries it into to Mars, one small stroke at a time. So it's going, our best rate that we've ever seen on Earth was about maybe 1 to 2 millimeters per stroke. So it's not super, super fast, but it's very effective. So you can see as it goes down, never goes that fast, but it sends out this heat pulse, waits to see how long it takes for that heat pulse to dissipate, and then continues down. And it keeps doing that over time and building up that topology. So that didn't go quite as we had planned. Let me go back for a second. So that didn't go quite as we had planned. So we had hoped that it would penetrate maybe at that something close to that speed over the course of months, but it didn't do that. So what happened is we got about 15 centimeters real fast, and then it more or less slowed way down. We did a couple of different hammering cycles, and we ended up with it, what we believed was stuck out of the ground about 5 centimeters. And it's about half a meter long, so about 50 centimeters. So it was still out a fair amount, and it wasn't moving at all. And so we scratched our heads for quite a while trying to figure out what we could do. We did a bunch of experiments, a bunch of tests, tried a whole bunch of different things, and then we decided we really just didn't know enough about what was going on. And so we started what we called the mole recovery activities, #SaveTheMole. And the very first thing we did is we had to lift the support structure off, to see what was going on. And you can kind of see, if you look real close, there's the mole. And it's in a hole, which we call the mole pit, or the pit of doom. And interestingly, the soil properties on Mars are very odd because it's about 5 centimeters of no soil, and there's no lip on that little hole. So where did the soil go? Basically it got pounded back into the ground. So it seems like it's very cohesive, even though it's very dusty. So now we got to see what we have, and we really scratched our heads thinking about what to do next for a while. And we thought, okay, let's try to fill that pit up. So we tried that. You can see the animation up here, pictures from Mars. So we first pushed with the flat edge of the scoop that we have on the end of it, and then we pushed with the sharp edge of the scoop. We got a little bit of dirt in the hole, but really not too much. If you look across here, some of our different attempts, pictures after the attempts. You can see there's a large number of days between the sols. That's because it does take a long time for the data to get down and then for us to look at it and decide what to do next. So that was interesting. Soil mechanics people loved that, but it really didn't solve our problem a whole lot. We did get a little dirt in there, but not nearly enough to start hammering with the mole, because there were two theories I should have said early on. Is either we hit a rock and we're not going anywhere, so there's nothing we can do anyway, or we were hopeful that what we had actually done is somehow lost friction in the soil, given that there's a big area with no friction touching the mole. We were hoping maybe that was the problem. We need friction because in that animation that you saw, we have the big, like 100 Newton force down, but then we still have about a 7 Newton force coming back up. And so we actually did some experiments on Earth where when we didn't have quite the right conditions, the mole could actually either bounce or even come back out. So without enough friction, we were thinking, well, that's the only thing we can do anything about, and we were hoping that that was the problem. So we got to about this point right before Mars solar conjunction. We couldn't do anything for roughly a month. We thought a lot, and we decided when we came back we're going to try something completely different. We're going to try to pin the mole using the scoop. So we did this operation here where we pushed horizontally against the mole, and then we vertically pushed down, and essentially trying to give it some friction force to make it, to allow it to hammer. So we did that, and then we got surprising results. It actually worked. So if you look, I think you can look here, it's actually going down. So that was our first hammering attempt, just 20 strokes. We got about half a centimeter, which doesn't seem like much, but we hadn't gotten any for months. So for us, we were very excited. And so we've been continuing to do that. Here's sort of a stitch together of the last few. We got another command in last week I didn't have a chance to put in here, but we got another probably centimeter or so. And we're getting close to the point where we're actually almost into the soil. We're going to probably move the scoop away, and maybe the mole will continue to go, which is our hope and dreams that it does that. So it's been very interesting, exciting problem, trying to solve a problem on Mars that you don't have a lot of visibility in or knowledge of what's happening. The soil properties are very different than anything we've ever seen on Earth, which is already a very interesting result. Okay, so I'm kind of running out of time. This is the complete recovery movements, but I'm going to skip this one. Give you a picture of sunrise on Mars. So there's the sun coming up. In case you missed it, it's right there. This is the arm. So this is taken from the camera that we have mounted on the arm. I'll let it go one more time because I think these are really cool. And then since we saw sunrise, we wanted to see sunset. And there goes the sun from Mars. And then when I'm having a really stressful day, I look at this. This is clouds on Mars. So it's pretty zen-like. And I just wanted to finish with a couple of things here, which is this is the team that's done all this amazing work. I get to talk about it, but these guys are truly amazing. We have our international partners. You can tell our French fellow here with his scarf. But we have people from France, Germany, Switzerland, Spain, the UK, all supporting us. And if you liked the landing show, you weren't the only one. Our landing show actually was so successful that we actually got an Emmy. So we won an Emmy for the best original interactive show. So that's me down there giving an acceptance speech. That's not something that you normally get to do as an engineer. I don't think I'll ever do that again. But it was a lot of fun to walk the red carpet and have that all happen. So anyway, thank you very much. That's the end of my presentation. And if there's anything that you guys want to know more about InSight, we have a great set of information on the web, so please feel free.
Now that the mold is recovered, are we going to be getting any measurements on soil properties other than thermal, like mechanical properties, porosity, as other than depth?
Yeah, so the question is, are we going to get other thermal other soil properties other than just the thermal properties? We plan to get those at the surface. We've done some soil mechanics experiments already in the course of trying to save the mole. We're not going to get any beyond the surface, but we're getting some right on the surface, which are already giving us some really interesting results I can't quite talk about because we have some science papers that are coming out. They're due to be released in the next couple of weeks, and I can't get ahead of the scientists, but please look for that. It's actually fascinating.
Cool, thank you.
Yeah.
To deal with the dust on solar panels, is the way of proceeding basically to over-design them by 100% and hope for the occasional wind, or has thought also been given to other means like a robotic arm with a sweeper or vibration or other ways to clear them?
Yeah, anytime you're trying to do something else robotically, the question is, have we thought about doing something better than just hoping that our solar rays don't stop working because of the amount of dust? Do we have an active mitigation? We did think about that. The problem is almost anything that you think of can create even more problems. It's a great idea, but it's very challenging to actually implement in a relatively low-risk manner. So what we did is what you suggested. We actually over-engineered them, and we increased the size of them by a factor of about 2, as you suggested, such that we would be fairly certain that we can make the full Mars year, which is our requirement.
Hello, my name's Alistair from Stirling University. How many of those 150 events have any been confirmed to be meteorite impacts or bolides?
Yeah, so the question is, of the 150 seismic events I've mentioned, how many of them have been determined to be an impact or something other than a seismically generated structural event? We've been trying to track to see if we can correlate meteor impacts. We do get some idea of meteor impacts from MRO. With any of those events to date, as far as I know, we have not been able to do that, which is a little bit of a surprise. We thought that we'd be able to correlate some of those, but we haven't yet. I think the answer is going to be we're going to figure that out a little bit later, that some of those actually were impacts, but we have not yet, which is a little bit of a surprise. Yeah. Absolutely. And if you have further questions, I'll be around.